Morning again, everybody. So let's start off where we left off, which was right here. We're talking about how to calculate net force. That's a fairly simple example, and a little bit later we'll look at some examples where we have forces that are not conveniently lined up in the same plane. But let's have a little talk about how we relate that to what we were talking about the other day, to do with Newton's laws of the bloody obvious. And the first law, the law of inertia, is the one that says things won't move unless you force them to. The second one, though, that's the one that says that things move faster if you push them harder. Now, I was using faster as a kind of simplistic way of implying acceleration yesterday, because it's really acceleration that is important here. A net force will cause an object to accelerate. And we also mentioned that if you have an object that is heavier, it will accelerate more, it will move faster. Now, heavier is not the right term either. Really, what we should be talking about here is mass. And a little bit later on, we'll do a lab where we disambiguate the two terms mass and weight. When we talk about how heavy something is, we are generally referring to its weight. And we are very specific in this case. It's mass that is important. And we'll see over the next few days why it is so important that we get those terms right and use the correct ones when we are doing these problems. So essentially, what we were saying with Newton's second law is that acceleration, or how quickly something starts moving off, is going to be equal to how hard you push it, right? Harder you push it, the more it accelerates. Those are directly proportional. But if it is, inverted commas, heavier, by which we really mean mass, if the mass is bigger, then it will accelerate more slowly. So it's inversely proportional to mass. That is the mathematical definition of the concepts that we were talking about yesterday. And we can make use of this. We can rearrange it, first of all, and this is the form in which you will generally see Newton's law written down. Net force is equal to mass times acceleration. In conceptual terms, to define it, though, we should think of it as the acceleration is directly proportional to the net force, inversely proportional to the mass. This is the form that we'll use most often, though. Okay, we can make use of that to figure out what the units must be for the force, because the units of force must be equal to the units of mass times the units of acceleration. And let's see what all of those are. We'll leave a blank on this side, and then we'll put in a space for the unit of mass, and then a space for the unit of acceleration. Mass, we know that one, kilograms. Acceleration, we also know. That is meters per second squared. So what do we get when we put all that together? Well, we get kilograms times meters divided by second squared. So the unit of force is the kilogram meter per second squared, but it would be really annoying if we had to say that all the time. So instead, we have defined the kilogram meter per second squared as being the Newton. So we can talk about newtons instead of kilogram meters per second squared. All right, so let's address situations where we have forces that are not neatly lined up on the same plane. A fairly simple example might be if we have two forces acting on an object, and those two forces are acting at 90 degrees to each other. And we want to combine them into one single force. Well, we've already looked at examples of this, and it's exactly the same process. This here, let's give that a value of 10 newtons, and let's give this one a value of 8 newtons. In order to add two vectors, rule 1 is we draw the vectors nose to tail in order to figure out what their sum would be, right? So I'm looking for the sum of those forces. So net force equals. Conceptually, what I'm doing is I am taking each vector one at a time. So take that one. Then I take the second one and I put them nose to tail, like so. And then I figure out the line that goes from the very beginning of the first one to the very end of the third one. And then whatever that line is, once I know it, I put it back over here, and that is my answer. Okay, that's what I'm doing conceptually speaking. I have to go to the trouble of moving all of those arrows all over my page because there is a mathematical shortcut that I can use, and that is that no matter what order I arrange those vector arrows into, you're always going to make a right triangle, and you're always going to make a right triangle whose hypotenuse is equal to the diagonal of this rectangle. And furthermore, if the value of this vertical black arrow is 8, then that must be 8 also. And likewise, if the horizontal black arrow is 10, then that must also be equal to 10. So first step is knowing that the net force is going to be the length of the red arrow, which obviously is going to be 8 squared plus 10 squared square rooted, which we worked out earlier was, I think, 12.8 newtons. And then in terms of direction, well, where are we measuring it from? If we're measuring it from the horizontal, it would be that angle there. You could measure it from the vertical, that would be fine. Let's measure it from the horizontal though. And like we said before, we'd have tan theta equals opposite over adjacent, so that would be 8 over 10, right? 8 over 10. Giving us theta equals the inverse tangent of 8/10. And that was, let me see, what was it? Inverse tangent of 8/10. 38.7 degrees. So that's how we would find the net force acting on that object. Okay, what say you we look at a crazy example now. Let's have a box that's being pulled in all kinds of different directions, none of which are conveniently located on the X or the Y axes. And we want to figure out what the overall force acting on this box is, and we want to know what direction it's acting in. We can't do that without knowing some angles, so let me put in a couple of those for us. I'll just draw in a horizontal line. Excuse me, just draw in a horizontal line here so I can mark some of these. Let's make that one. That looks like about 60 degrees. That looks at about 20 degrees, and that looks like around 70 degrees. So, find the net force is our challenge. Find sigma F. How on earth are we going to do this? Well, the strategy here is to find the total up or down, and then the total left or right. We need to find the components of each of these vectors and then add up all the X components, add up all the Y components. If that doesn't make sense to you, hopefully it will as we go through. So this first vector here, this one, let's go with that. Oh, we need to know the size of these also, don't we? Silly me. Let's see. Let's call that one 18 newtons. 20 newtons and 21 newtons. So let's start with this 18 newton vector here. Well, it's pulling us to the right a little bit, right? Because it's pulling us that way, but it's also pulling us that way. And most of its pull is probably up rather than across. but it does have an effect in both x and in y. In other words, it has an x component and a y component. And we want to find the total amount of x and the total amount of y. If we just focus right now on just the up-down and look at these forces, then the 18 Newton is pulling up, the 20 Newton is pulling up, and the 21 Newton is pulling down. And so the question is going to be, who's going to win that tug of war? Is it the 20 and the 18 up and the 21 down? Now, obviously, 20 plus 18 is bigger than 21, but not all of this 20 Newton vector is pulling down. In fact, most of it's pulling across. Not much of it's pulling up at all. So the question is, does the component of the 20 Newton vector that is acting upwards plus the component of the 18 Newton vector acting upwards, does that outweigh the 21 Newton vector component acting downwards? Now, instead of saying up-down, we're going to talk instead of x and y, which amounts to the same thing. So what we're going to do is find the x and y components of each force vector. And I'm going to list them. Okay, I've got the 18 Newton vector, I've got the 20 Newton vector, and I've got the 21 Newton vector. And each will have an x component and a y component. I'm just going to put these into a little table. All right, straightforward enough. If you don't remember how to find the components of vectors, then look back on that previous video on vector components that was posted in the last block. The 18 Newton vector component, the 18 Newton vector is connected to the x-axis, so the x component will be the cosine one. So it's going to be 18 cosine of 60. And therefore, the y will be 18 sine of 60. We need to think about sine here. The 18 Newton vector is pushing to the right in x, and it's pointing up in y, both of which are positive. If we look at the 20 Newton vector, well, it's connected to the x-axis, so the x component is going to be the cosine one, and therefore the y component will be the sine one. Let's think about the direction. This 20 Newton vector is pushing me to the left in x, so negative in x, but it is pulling me up in y, so that is positive in y. And finally, the 21 Newton vector, well, it is connected to the x-axis again, so that's 21 times the cosine of the angle, so 21 cosine 70, which means the y1 will be 21 sine of 70. Now, just because all of the y's were sine in this case, don't assume that that will always be true. You always have to check which component is which. Now, in terms of direction, well, the x-axis component here is acting to the left, right? This 21 Newton is trying to pull us to the left, so that's going to be negative. And in y, it's trying to pull us down, so that is also going to be negative. What this allows us to do, is to then find what our totals are. And we can say, what are the total components in x and the total components in y? So I'm just going to find the value of these three numbers, 1, 2, 3, and add them together. So I've got 18 cosine of 60, which is 9, plus the negative of, so that's going to be subtracting 20 times the cosine of 20. And then I also want to subtract 21 cosine 70. So I've got 9 minus 20 cosine 20 minus 21 cosine 70. And that gives me an answer of negative 2.6 newtons. And I do the same thing for y. I've got 18 sine 60 plus 20 sine 20 plus, minus at the end, 21 sine 70. And that gives me positive 2.7 newtons. The fact that those two numbers are similar is pure coincidence. Now, what I've done there is I have worked out that these three vectors could all be replaced, all of them, with two vectors, one of which is lined on the x-axis and has a value of 2.6, and one of them which is lined up on the y-axis and has a value of 2.7. My x1 is negative, so it would be to the left, and my y1 is positive, and so would be upwards. And the value of these would be 2.6 newtons, 2.7 newtons. The question, though, was find the net force. I haven't yet found the net force, but what I've done is I have allowed myself to easily calculate it because I know that the net force in this situation will be that green arrow, and finding the length of that green arrow and its angle is relatively straightforward. So let's just do that to finish off this little problem. So first of all, I know that the resultant vector, adding those two together, is going to be 2.7 squared plus 2.6 squared, all square rooted. And that's easy enough. Well, it's easy enough if you hit the right button on your calculator. .75 newtons. Then the question is, what direction is it acting in? And this, the angle's easy to calculate, but describing it's going to be a little bit tougher. And we'll talk about some of the alternative ways in which we can do that. So if I just take my two vectors, I'm just going to redraw them over here, slightly different scale, just so I can 2.7 newtons, 2.6 newtons. We know that the resultant vector is the one that kind of completes this box here. So it'll be this blue arrow. We just worked out the length of it. It's 3.75 newtons big, right? 3.75 newtons big. Now, in terms of describing the angle, where should we measure it from? Should we measure that angle? Or should it be this one? It's up to you. As long as you're able to describe where the angle is measured from, you can quote any angle you want. Let's do this one. So tan theta will be opposite, which will be that side, and that side must be the same as that side. In other words, 2.7 over adjacent, which is 2.6. Theta is the inverse tan of 2.7 over 2.6, which is 46.1 degrees. And then finally, if we needed to describe that to somebody, where did we measure it from? So our final answer would be the net force is equal to 3.75 newtons at 46.1 degrees from where? Well, in this case, we're measuring it from negative x. So measured from negative x. And one more problem, 46.1 degrees from negative x. Well, negative x is that direction. That's done. Don't need to amplify, or sorry, don't need to say any more about that. However, that angle is also at 46.1 degrees from negative x. Which one do we mean? Do we mean the one below negative x or above negative x? And in this case, it is above. So we could say measured at 46.1 degrees above negative x, or you could use directions in terms of clockwise and anti-clockwise, in which case, if we're starting at negative x, we are going clockwise. So let's say 3.75 newtons at 46.1 degrees measured clockwise from negative x. And there is our final solution.